Hello, we're going to be looking at particle heat transfer. This is where heat transfers in the macroscopic world with what we can see and the atomic world with what we can't see and how this actually occurs. There's going to be three parts: the modeling, which is drawing, the description, which is describing, and explanation, which is explaining why this actually occurs. All three parts are what we're trying to get to. So let's take a look at the macroscopic world. So when we have the macroscopic, we have a source of heat, like this burning tire brake, and it's going to transfer energy from it to the surroundings, like parts of the car, the air, and everywhere else. Such as when we open the fridge, heat from the surroundings can transfer to the cooler things like the milk. And if we just put the orange juice in, then the warmer orange juice can transfer energy to the cooler milk. Or like when you drop your ice cream on the floor, so sad, the warmer cement will transfer its energy to this. I'm just using arrows. And these arrows show where the heat is most, right when we start it, and it ends up where it's the least, or the coolest part. This will always go from the highest temperature to the lowest temperature. So something that is cool, like our ice cream, is going to have the ending of the heat transfer, while the surroundings, which are warmer, are going to end up its heat in the cooler substance of the ice cream. This is what we do with the macroscopic. So you have a general writing or tendency, and you're going to recreate these in your notes, with showing arrows as heat transfer. At the atomic, it's a little different. So in this case, you can model this a couple different ways. You can either model it with spheres and arcs, circles and lines, or circles and arrows. Now, I prefer circles and arrows, although all three are perfectly acceptable. The idea is that the colder particles are shown with less arcs, while the warmer particles are shown with more arcs. The cooler particles have shorter lines of movement. Warmer particles have longer lines of movement. Over here, we have the idea that the circles with longer arrows are moving faster. Circles with shorter arrows are moving slower. So slower and less energy, faster and more energy, slower and less energy, faster and more energy, slower and less. So particles, in the end, after they collide, after they have transferred their energy, should have the same amount of arcs. Or over here, they should have the same length of these lines. And over here, they should have the same length of arrows. So everything in the end, after energy is transferred, will all be the same. And so that's pretty important when we talk about that, because then after everything is the same, then there will be no more kinetic energy transferred, no more kinetic energy transfer, no more heat transfer. Technically, the spacing of the particles will help indicate if it's like a solid, liquid, or gas, but we're not going to go that far. We're going to use the same model for solids, liquids, or gases, just for simplicity manner, because again, we're just trying to model heat transfer, not really trying to model the difference solid, liquid, and gases. Continue on to the next one, labeling description, so you can get a complete understanding of heat transfer.